So last time we talked about physical quantities and we talked about fundamental quantities, 7 fundamental quantities. And we also talked a little bit about derived quantities. So we have 7 fundamental quantities. Out of 7 fundamental quantities, we'll be mostly focusing on 3 in this course. Okay, so we'll be dealing with length, we'll be dealing with time, and we'll be dealing with mass. So length is denoted by L, time is denoted by T, and mass is denoted by M. So these are the fundamental quantities or basic quantities. And all the other quantities that we deal in physics are based on these quantities. Okay, so they are also called derived quantities. For example, like last time we talked about area. Area is length times length, so it's length squared. So it's derived from length. Okay, so that's why it's derived quantity. Likewise, speed. Speed is denoted by distance traveled per unit time. Distance is length, kind of length, so it's L, and time is T, so it's derived from length and time, so it's a derived quantity. So likewise, we can have work. Okay, so we'll talk about this more in the next chapters. So work is the product of force and distance. Okay, you don't need to know the formula, but I'm just giving you the formula here. And force is mass times acceleration, and this d is d. Okay, mass. Acceleration is rate of change of velocity, how the velocity is changing or how the speed is changing. So it's speed over time. Okay, that. So mass is m. Velocity, we just saw that velocity is L over T. It's a derived quantity, L over T. So that's for the velocity. And then we have another T here. So this T and this T. So this T also has T. So we have T squared. And we have D here. D is also kind of length. So L. Okay. So we have M L squared over T squared. You see, that's the quantities involved in work, okay? And they are all derived from the fundamental quantities. So we have many different quantities in physics. Most of them are derived quantities. And the number of quantities involved in this expression is called dimension. Okay? So number of quantities involved in this. So here we have mass, length, and time. So this has 3 dimensions. Okay. Likewise, here we have length and time, so this has two dimensions. So sometimes we can use the dimensional analysis to see whether a given formula is correct or not. So for example, let's say we have a formula given. Say we have this formula, V is equal to, so V final velocity is equal to initial velocity plus 1/2 acceleration times t squared. Okay. You don't know about this formula, that's fine. We just want to apply dimensional analysis to see if this formula is correct. Okay. So the dimension of velocity is same as the dimension of speed, because speed and velocity are almost same, except one has direction and the other one doesn't have direction. So in the next chapter we'll talk about that. So here you only need to know the dimension of V is L over T. Okay? So it has two dimensions. It involves length and time. So that's the final velocity. On the right side, again we have velocity. So that's the initial velocity. So same dimension, L and T. Plus, if you have a pure number doesn't have any dimension. Okay, so it's dimensionless. So you don't need to worry about that. And then acceleration, we just saw here, acceleration has this dimension. This is the dimension for acceleration. Okay, L over T squared. So acceleration is defined as change in velocity over time. Okay, we'll talk about that in the next chapter again. So we don't need to know more about that here. We just need to know what dimensions are, or what physical quantities are involved in this. So it has V is L over T, and then we have another T here, so that means it involves length over time squared. Okay. So again, this V is L over T, and this is T. So L on the top, and T on the bottom, so that's T squared. So we have L over T squared for acceleration, and then T, this is the time. Okay, so time is T squared. Now you see, you can cancel this one and this one, because you have T squared and T squared, they are same. If you have same thing on numerator and denominator, you can cancel them. So you have L over T plus L. So on the left side you have L over T, on the right side you have L over T plus L. So this is dimensionally incorrect. Okay, so you need to have same kind of dimension for them to be for them to be to be able to add. Okay, so if you have different dimensions here, like you have L over T and L, you cannot add them. It's like adding apple and orange. Okay, so you need to have same dimensions. So this formula is not correct. Okay. So you can know that just by using the dimensional analysis, you can say that this is not a correct formula. Okay. So let's see another example. So we have this formula. So time period of a pendulum is given by 2 pi over square root of L over G. Okay. So this is time. Okay, time, the dimension of time is T, and 2 pi is a number, it's a pure number, so there is no dimension, it's a dimensionless. And then we have square root L, the dimension of L is L. Now G, okay, so you haven't seen G yet, but we'll talk about this later in coming chapters. So G is kind of acceleration. It's called acceleration due to gravity, and it has the same unit or same dimension as the dimension of acceleration. And we saw here the dimension of acceleration is that, okay? This is the dimension of acceleration. So it's L over t squared. So G has the dimension of L over t squared. So you can cancel this L and L and then move this t squared to the top. Okay, it goes on the top. So then you get t squared, and then you cancel this square root and square, and then you get t. And you see that you have t on the right side and t on the left side. So that means it's consistent. So this means this formula is correct. Okay. So that's how you can find if a given formula is correct or not. So there are a couple of homework questions that involves dimensional analysis. Okay, so the next thing we want to talk here is scientific notation. So often in physics you will see either a very large number or a small number. So you don't want to write a large number or a small number or include all the numbers in your writing. So you want to condense the large number into smaller notation. So how you do that? Let's see that. So here we want to talk about scientific notation. So let's say you have this number, okay, so 0.0000314 seconds. Okay. So you don't want to write this long number when you do the calculation. Or let's say you have another number, let's say 917.3 and 0.0000 Newton. Okay. So often when you have long numbers like this, what you do is you move this decimal after the first non-zero digit. So here our non-zero digit is 3, so you move this after that, okay? And then all these zeros become irrelevant. So you have 3, okay, that is the 3, and then you have this decimal is moved here, and then you can write the number here, okay, 3.14. And then when you shift the digit decimal to certain digits, what you need to do is, if you move it to the right, then you need to put minus sign here, okay? Because it's a small number, smaller than 1, so we'll have 10 to the power negative here. And then see how many digits you shifted it by. So 1, 2, 3, 4, 5, 6. So you moved it 6 digits to the right. So that means you need to put negative 6, okay? So that's how you express this in this kind of scientific notation. Likewise here, you write the first digit and then put your decimal here and then write the non-zero numbers. And then if you have no decimal here, you consider the decimal is at the last, after the last number, okay? So here is your decimal. So you are shifting your decimal how many places to the left. So 1, 2, 3, 4, 5, 6, 7. So you're moving this 7 places to the left. That means since it's a bigger number, so we'll have a positive power. So 10 to the 7 Newton. Okay? Like that. Now when you have numbers like power like this or this, so sometimes instead of writing the powers, you can also give some name. Okay, so the names are, if you have, let's say, power, if you have 10 to 15, if you get, let's say, 3.15 times 10 to 15, something here, then you can write that as 3.15 peta P, capital P, let's say second. Okay, so that's called, name for this one is peta, and symbol is capital P. If you have 10 to 12, it is tera. Like you have hard drive of 100 terabyte or something like that. So that's tera. That's 10 to 12 bytes, 10 to 12. And that's capital T. If you have 10 to 9, it's gigahertz or gigabyte. Okay, so that's capital G. If you have 10 to 6, that's mega. Like in a radio station, you have megahertz. That's 10 to 6 hertz. So that's M, capital M. If you have 10 to 3, it's kilo, small k. If you have 10 to negative 2, you should know that. That's centi, like centimeters, centigram. So that's small c. If you have 10 to negative 3, you can write that as millimeter or milli. I mean, for example, if you have 1.1 times 10 to negative 3 meter, you can write that as 1.1 millimeter. Okay, so this 10 to negative 3 is millimeter or milli. If you have 10 to negative 6, you can write micro for that. It's a Greek letter mu. 10 to negative 9 is nano, small n. 10 to negative 12 is pico, small p. And 10 to negative 15 is femto, it's small f. Okay. So if you have some expression like this, like 2.17 times 10 to 7, let's say kilogram, so you can write this as 21.7 times 10 to 6 kilogram, and then you can call that 21.7, this is mega, okay? Mega kilogram. Another important thing that we'll be using very often in this course is unit conversion. You might have done that in high school or in some math course. So let's talk a little bit about how you do the unit conversion. So unit conversion. Let's say we have 29 days. Okay, and I want to convert that to seconds. So how many seconds are there in 29 days? So to do that, You can always multiply numerator and denominator by 1 without any consequence, okay, because that doesn't affect the actual value, so you can do that. And you can on the denominator you can put the same unit as the unit that you want to get rid of. Okay, you want to get rid of day, so you put day on the bottom here and write the conversion on the top. So 1 day is how many hours? 24 hours, right? So you can put that here, 24 hours. Okay. 1 day and 24 hours are same, so they will cancel to give you 1, so this won't affect our original number. And then we also want to convert hour, okay, so we want to get rid of hour, so put 1 hour down here. And then 1 hour is 60 minutes, because this is also 1, so this is 1, it's just multiplying by 1. And then we want to get rid of minutes, so put minutes down here. And then 1 minute is 60 seconds, and that's what we want to get. Okay? And this is also 1, so it won't affect our original number. It's just multiplying this number by 1, 1, 1. And then, so hour and hour cancel, minute and minute cancel, day and day cancel. So you get 29 times 24 times 60 times 60 second. Okay? So that will give you 25056. Something like that, or yeah. So that's the number you get. Now you don't want to write the number like this. You don't want too many digits. So like before, we will express this in scientific notation. So write the first digit and then put the decimal after that, and then write 1 or 2 digits. Okay, you don't want to write too many digits here. 1 or 2 would be fine. So let's say 2.50, and then our decimal is here, and we are shifting this by how many places here? So 1, 2, 3, 4, 5, 6. So we are moving this 6 place to the left. So 10 to 6 seconds. Okay, so that's the number of seconds in 29 days. Likewise, we can convert, let's say, meter to inch. So let's say I want to convert meter to inch. So 1 meter I want to get rid of meter, so put meter down here. And the thing I know is 1 meter has 100 centimeters. Okay? So 1 meter is 100 centimeters. And I also want to get rid of centimeters, so I'll put the centimeter down here. And we know that 2.54, we know 1 inch is 2.54 centimeters. Okay? So that means I need to put 2.54 here, because that's what I know. Okay? So instead of 1, I will put 2.54 here, 2.54 centimeters. And 2.54 centimeters is 1 inch. Okay? Again, this thing is 1, this thing is also 1, so multiplying our original number by 1 and 1 won't affect our actual number. So now we cancel centimeter and centimeter, meter and meter, so we have 100 divided by this number 2.54, which is 39.3 37 inch. Okay. So that's how you do the unit conversion. So there are a couple of homework questions where you will need to do this kind of unit conversion. Okay. So let me show you the homework question. It's on export T. So again, if you haven't registered this export TA, please do so. There is one homework already posted. It is due next week, next Friday. You will need a code to register this. Okay. So here is homework 1. Let's see. So this is about the unit. We'll talk about that in a second. So here is an example of the conversion. So it's asking you to convert 95 miles per hour to kilometer per hour, okay, and also to kilometer per second, and also to meters per second. So do the same kind of thing for this conversion. So if you don't know the relationship between miles and kilometer, you can Google that. So let me just show you one, how to do that. So we have 95 miles per hour. So 95 miles per hour, or let's just use the MI, miles per hour. So here we want to get rid of miles, okay, so 95 miles over hour, so put the mile on the bottom. And we need to see the conversion factor between miles and hours. How many miles and kilometer? So how many kilometers are there in 1 mile? Does anyone know? If you don't know, you can Google that. Okay, that's fine. So I think it's 1.6 kilometers. Miles into. So 1 mile is 1.609 kilometer. We can just write 1.6 kilometer. Okay. So 1 mile is 1.6 kilometer. And then mile and mile cancel. So you have 95 times 1.6. We have kilometer on the top and hour on the bottom. So you multiply that, that'll give you the unit in kilometer per hour. Okay. And in the next part, it's asking you to convert this into kilometers per second. Okay. So for that, you need to use the conversion for hour. So you want to get rid of hour, so put 1 hour on the top here, and then 1 hour is 60 minutes. Okay, here is a number, there's a number on in front here, and then 60 minutes, we want to get rid of minutes, so 60 minutes is, to get rid of minute, you put minute on the top here, and then 1 minute is 60 seconds. Okay, so Cancel hour and hour, minute and minute. Then you get some number, kilometer per second. Okay, so that's how you do the conversion. Now let's talk about units. So there are a couple of questions in the homework where you will need to find the units of the derived quantities. So we saw the three fundamental quantities: length, mass, and time. The unit of length is meter. It's the standard international unit. Although in real life we also use miles or inches, but in physics we often use meter for the length. Okay, so that's what we use. It's small m. For mass we use kilogram, kg, and for time we use second. So this system of units is called international system. Or it's also called SI unit. That's what we use in physics. And we can write the units of other derived quantities, okay, in terms of these fundamental units. These are fundamental units. So here, let's see a question. So you are given these quantities here: mass, distance, height, and then you are given the units here: kilogram, meter, okay, time, and with that it is asking you to find the unit of the given quantities. Or in this question it's asking you to see if the unit is consistent on right and left. Okay, so you have this formula: v squared is equal to 2ax. So you need to find out if the unit on the left is same as the unit on the right. So let's look at that. So v squared is 2ax. So we have this formula: v squared is equal to 2a. What is that? X. Okay, on that table you can find the units for all these things. Okay, so the unit of v is meters per second. We have square, and then on the right we have 2. The unit of a is meters per second squared. It's given on that table. And then x, unit of x is meters. And see if the units are same on left and right. So meter and meter is meter squared, second squared. So you can write that as 2 meter per second squared. Okay, so that means the unit on the left is same as the unit on the right, so it's consistent. So that's what you need to do for all the questions on this one. Okay, and then this one is the dimensional analysis. So you need to figure out which of these are consistent dimensionally. Okay, just like I showed before. For example, let's see if this one is dimensionally consistent or not. So v squared is 2ax. So let's look at that. V squared is 2ax. So v squared is 2ax. So v, the dimension of v is L over t. And we have square, so it's L squared over t squared. The dimension of a is L over t squared. Okay, that's what we've got in the previous discussion. So a is L over t squared, and x is just the position, it's kind of a length. Okay, so length is L, so that means 2 L, and L is L squared, and T is T squared. So we have L squared over T squared on the left, L squared over T squared on the right. So it's dimensionally consistent. Again, this one, there's no dimension for a pure number. So same on left and right. So you need to figure out which of the given formulas are dimensionally consistent. Okay. Any question so far on the topics that are covered so far? Okay, so the next thing is uncertainty. In physics, we do lots of measurement. Physics is all about measuring the physical quantities. Okay, like we measure length, we measure speed, we measure mass. So physics is all about measuring physical quantities. So when we measure the quantities, we get a number in terms of some unit. Let's say we want to measure a length of something, let's say this arrow. So how do you measure the length of this arrow? So you take a ruler and put it near this arrow. Okay, so align the edge of this ruler with 0 mark of this ruler with the edge of this arrow, and then put it like that. So that's the ruler, and the ruler has markings or divisions. So let's say we have 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 0, this is 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, and so on. And this is 1/10 of the centimeter. Each of these divisions is 1/10 of the centimeter, or you can also call it 1 millimeter. So when you measure that, so see where this one aligns with the division. So let's draw a line here. Let's blow it up. Okay. So we know for sure that it crossed this mark. Okay, so the first number is 3, and then it also crossed this smaller division. So 1. Let's do that. So it crossed 3, and then we also have 1, 2, 3 of these smaller divisions, and then we have the line between this third line and the fourth line. So it's like this is the line I have, and this is between this third line and fourth line. So there is uncertainty there. You don't know for sure what value this is indicating. So you need to make some kind of guess here. Okay? So imagine that there are 10 divisions in between 3 and 4, and see which of these divisions this line aligns with. So let's say it aligns with 5. Okay? So you write the measurement like this. So this number is what we call uncertain number, because it's the guess number. Okay, you get this number by guessing the position of this pen or the arrow. These are the certain numbers. These two are, you know for sure, these are crossed by the arrow. So these are certain numbers. So that means in physics measurement, there's always some kind of uncertainty. You don't know the exact value of a measurement. So how do we denote the uncertainty? That's what we want to talk here. So in physics, when you express a number, we'll talk more about this when we do the lab next week. But for now, let's just talk about how you represent an uncertainty in a number. So let's say you have a number 3.14, and you know that this is not the exact number. So there is some uncertainty in this. So uncertainty is represented by plus minus 0.0 something. Okay, so let's say 2. So this is uncertainty in your measurement. And this, the meaning of this is, the number you are writing here is not exact, and the number could be in between 3.14, 3.2 and 3. So you add and subtract this from that, this with that, so 3.16. So you don't know for sure what the number is, but you know that your number or your measurement is between this one and this one. Okay, that's how you express the number in physics. And the number you have here, these numbers are what we call significant figures. Okay. Sometimes people write 3.145 like that, so you cannot write long number like that, because your instrument can only measure up to 3 digits like that. Okay, it can reliably express only 3 digits, so that's the significant figures. So significant figures are very important in physics. It tells you how reliable the instrument is. So if you have a number 3.1, 3.45, 3.456, you can tell which one is more accurate, which one is more reliable. So this one has more sigfigs or significant figures, so the equipment that yields this number is more reliable. So how do we determine significant figures in a number, given number? So let's say you have a bunch of numbers, 3.145, so you have a number like that, you have a number like 2.209.4, you have a number like 0.543, you have a number like So how many significant figures are there in each of these numbers? How do you determine that? So let's talk about that. So we have some rules that can tell us how many significant figures are there in a number. So the rules are, the first one is, if you have zeros at the beginning of a number or on the left side of a number, then they are non-significant or insignificant. So zeros at the beginning of a number, or that means the zeros on the left side of a number, they are not significant. So for example, you see here in this one, these zeros are not significant. That means only these three numbers are significant. So the number of significant figures in this one is 3. Okay. So there are 3 significant figures. So 5 is significant, 4 is significant, 3 is significant. Likewise, if you have 0.000303 like that, so these are not significant. You only have 3 significant figures. So zeros between or within numbers are significant. For example, you have 303, so this 0 between the numbers, okay, non-zero numbers are significant. So if you have 303, it has 3 sig figs, 3 significant figures. Likewise, here you see this 0 is significant, okay, because it's between 2 non-zero numbers. So that means this one has 4 sig figs, 4 significant figures. The third one is zeros at the end of a number after the decimal point are significant. Like in this one, this 0 comes after the decimal, so that means this is significant. Okay, so this one has 1, 2, 3, 4, 5 significant figures. Likewise, if you have 2.00, these zeros are significant. So this one has 3 sig figs. So that's about the significant figure. I think we have only a minute left. We'll talk more about this in the next class or in lab. So that's all for today. If you have any question, you can ask me the question. Otherwise, we'll meet next week. Have a great weekend.